Hello, in this video we'll be going over a rather counterintuitive example demonstrating that a derivative being positive at a point is not strong enough for the function to be increasing around that point. So it kind of breaks apart this intuition, at least that I had when I took calculus, that if the derivative is positive at the point, it must be increasing. There are conditions you can put on the function. If the function is in class C1, meaning that its derivative is continuous, well then if the derivative is continuous, then if the derivative is positive at the point, there's a whole open neighborhood where it would be positive just from the continuity of its derivative. But if you relax the condition, it's not necessarily true, and this is a counterexample. You get 2 for the price of 1 here. You get that also that you can see a function which is not continuously differentiable. So let's go ahead. So this is our function defined from -1 to 1 to r, piecewise by x over 2 plus x squared sine of 1 over x when x is not equal to 0, and 0 at 0. And here's a graph of the function. As you can see, away from 0, you clearly have intervals where it's increasing and decreasing, right? It decreases, increases, decreases, increases, and so forth. But what's happening is they're becoming smaller and smaller, and they're happening more frequently. And this is due to the 1 over x here. So you can see as you zoom in, it almost looks like a straight line because it's happening so frequently. So there can be, from a geometric point of view, there's no way that there would be an interval where it's increasing because it would be oscillating really like crazy or so frequently around 0. So that's the geometric. But what about the proof? So let's prove it. So the first thing we'll need to do is find what f prime is. So, well, f prime of x away from 0, we know that there's no doubt about it that the function away from 0, well, it's defined this way, and this thing here is differentiable by itself. So we know how to do that. It's just calculus 1. It's, well, what's the derivative of 1 over x over 2? It's 1/2 plus the derivative here. Well, what's the derivative here? Well, this is the product rule, so it's, let's do 2x times sine of 1 over x plus x squared times cosine of 1 over x times -1 over x squared when x is not equal to 0. The thing is at 0, well, we don't even know that it's differentiable yet. It is. But how can we see that? Well, let's compute it manually. So the f prime of 0, by definition, if it exists, is equal to the limit as h goes to 0 of f of 0 plus h minus f of 0 all over h, which is equal to, well, f of h minus f of 0, this should say limit as h goes to 0, minus f of 0 all over h, which is equal to h over 2 plus h squared sine of 1 over h minus 0 all over h, and still, I forgot to write it, but limit as h goes to 0. And now we can just use some algebraic manipulation here. And so this is just the limit as h goes to 0 of 1/2 plus h sine of 1 over h, which is equal to, well, the limit of this piece is 1/2. That's a constant. And this piece here, well, sine in general is bounded by 1, and bounded below by -1. So as when you multiply by h, as it's going to 0, this thing goes to 0 by the squeeze theorem. It's equal to 1/2 plus 0, which is 1/2, which is certainly greater than 0. So this proves the first part, at least, that f prime, so f prime of 0 is equal to 1/2. So really this is our derivative function, when in general this is our function here, of our derivative. Derivative here is 1/2. We need to show that f prime of, or rather, sorry, we need to show that f is not increasing in any open interval containing 0. Any open interval from -r to r, it's okay that it's symmetric. And what can we say about the derivative on this open interval? Well, the thing is, if f were to be increasing on this interval, we know its derivative would have to be greater than or equal to 0. So consider, so f prime on r to r would be greater than or equal to 0 if f was increasing. And why is that? Well, it's just the definition of the difference quotient. Since the derivative exists, you can always take h to be positive. This is f prime minus f of x all over h. Well, assuming x x plus h is inside this interval, and x is also inside this interval, well then this piece here is positive because this is bigger than this. Why is that? Because, well, f was increasing, so x plus h is bigger than x, so this piece here is positive and h is positive, so this has to be, well, it may not be positive, it may be 0, but this would be greater than or equal to 0. And the limit, it would still be greater than or equal to 0. So to contradict this for the proof, we just need to find, say, x naught, an element of -r to r, such that f prime of x naught is less than 0. If we do this, we would find something that would contradict this piece right here, this derivative being greater than or equal to 0. So let's do that. So if we look back up at what our derivative was, it's this piece here, really, away from 0. So we can just find, so no matter what the r is, so, well, let's first clean this up. This cancels with this, and 1/2 plus 2x sine of 1 over x minus cosine of 1 over x. Now, if we can somehow make sine 0 and cosine 1, well, then this would be 0, and this would be -1, and we'd have 1/2 minus 1, which is -1/2, and we'd be done. So let's forget about -r to r right now, and let's think for a second. when is cosine 0? I mean, when is cosine 1? It's 1 at 0 or 2 pi or any multiple of 2 pi. So when is cosine of 1 over x positive 1? Well, it would be the only sensible choice, or a sensible choice rather, is minus cosine of 1 over, well, what we'd want is 1 over 2 pi. Right? Because then this would flip and we'd have cosine of 2 pi, and cosine of 2 pi is 1. And it also does this. It would be sine of 1 over 1 over 2 pi, which is sine of 2 pi, which is 0, times 2 times 1 over 2 pi, but it doesn't matter. This would be 0, and we'd have 1/2. And this is going to be 1/2 minus 1, which is negative 1/2. This would finish it. However, the thing we need is to make sure that this point we picked, 1 over 2 pi, is an element of minus r to r. What happens if we made r so small, smaller than 1 over 2 pi? What if you made r minus 1 over 4 pi, or you made r 1 over 4 pi? Well, then you would go, well, I know it's every multiple of 2 pi, and 1 over 6 pi is certainly in this interval. I can't pick 4 pi because 1 over 4 pi because it's an open interval, and you would see that it would work. But what about an arbitrary r? What if it's even smaller? Well, the trick is I can always, by the Archimedean property, I can always find an n small enough such that, I can always find an n large enough such that 1 over 2 pi n, so 2 pi times n, so go as many multiples of 2 pi as you'd want, take 1 over that, and you would hope that would be in your interval, and well, you can certainly find an n large enough that would satisfy this. So this would be an element of minus r to r, and you'd find that the f prime of 1 over 2 pi n is equal to minus 1/2. And this contradicts the fact that we would need it if it was increasing to be greater than or equal to 0. So this is a contradiction. So it's interesting, though, that even though a function has a positive derivative at a point, it's not a strong enough condition to guarantee that locally the function is increasing around that point. So this is it for this calculus / analysis video. Comment any of your favorite counterexamples in analysis. I study abstract algebra, but I always find it fascinating, the counterexamples in real analysis and in analysis in general. Thank you, and please subscribe.